Hello, I'm glad to present our ICCV2025 work, AcZeroTS, Active Learning for Zero-Shot Tissue Segmentation in Pathology Images. Histological examination of tissue pathology slides remains the gold standard for cancer diagnosis and prognosis. Among different pathological image analysis tasks, tissue segmentation aims at identifying diverse tumor microenvironment components that are essential for understanding cancer progression. Over the past decades, deep learning technology has achieved remarkable success in computer vision, which also boosts considerable interests in designing deep tissue segmentation models. Current tissue segmentation models are mostly trained in a supervised manner that requires heavy annotation efforts from the pathologists. However, due to the complex structure of the TME components revealed in pathology images, it is challenging to collect annotations for all possible tissue types. To address the above issues, several zero-shot segmentation methods are proposed which are trained only on seen classes and can segment unseen classes that are not available during training. However, training an accurate and reliable zero-shot tissue segmentation model still requires amounts of high-quality labeled data on seen classes, leading to high annotation costs for pathologists. In order to reduce the labeling costs, several active learning methods have been proposed that aim at querying the most valuable samples from the unlabeled pool for annotation. However, these research efforts have not investigated how to design effective query strategies in the ZSS tasks. Intuitively, in the setting of ZSS, the query strategy of active learning should attach equal significance to both seen and unseen categories with limited labeled data. Based on the above considerations, we propose AcZeroTS, a novel active learning framework for zero-shot tissue segmentation in pathology images, which is built on a VLM-based prototype-guided zero-shot segmentation model called ProZS. AcZeroTS can select the most valuable samples of seen classes for annotation and improve the performance on both seen and unseen classes during the inference stage. At each iteration of active learning for AcZeroTS, we select the most valuable samples from the seen tissue categories for annotation by considering the following three criteria: evidence-based uncertainty of unlabeled data, contrast among the labeled and unlabeled data, and complete summarization ability of the prototypes, where EUN and COT consider both uncertainty and diversity of unlabeled samples, and the criterion of CSA measures the summarization ability of the generated prototypes on both seen and unseen tissue categories. By incorporating the query data for updating ProZS, we could achieve better segmentation results on both seen and unseen tissue categories in the test set. ProZS integrates the pre-trained pathology visual language model with prototype learning for zero-shot segmentation on pathology images. It comprises a vision pathway for extracting visual features and a text pathway for encoding semantic information to guide segmentation. We use focal loss as the segmentation loss. To enhance the discriminability of the pixel-level features, we introduce a category-wise pixel-level contrastive loss to learn pixel-level representations across different categories. Next, we introduce our active learning selection strategy, designed to optimize sample selection for seen classes while enhancing the generalization ability on both seen and unseen categories. It consists of three key criteria: 1. Evidence-based uncertainty of unlabeled data, EUN; 2. Contrast among the labeled and unlabeled data, COT; and 3. Complete summarization ability of the prototypes, CSA. EUN and COT focus on selecting diverse and uncertain samples, while CSA ensures that the generated prototypes in ProZS effectively summarize both seen and unseen categories during inference. Considering the image with rich information is crucial for the generalization ability of the model, we adopt an evidence-based uncertainty estimation technique to avoid the issue that the traditional entropy-based methods tend to produce inflated confidence values, even for incorrect predictions. Specifically, for the unlabeled image, we calculate its score map without applying softmax. Then we adopt the ReLU activation function to derive its evidence map EJ. We connect the pixel-wise evidence to the Dirichlet distribution parameters with strength QJ, by which we can assign a belief mass QJK for each class K. In essence, the increased evidence supporting a class results in a greater belief mass being allocated to it. Based on it, the uncertainty map is formulated as UMJ, and thus the uncertainty score is defined as USJ. To increase the discrepancy of data, we resort to certain contrast samples in the unlabeled pool that exhibit higher feature similarities with labeled images, but result in significantly different category distribution. Intuitively, such samples are located near the decision boundary that are valuable for annotation. Specifically, for the unlabeled image, we firstly calculate its distance to all labeled pixel features and identify its k-nearest neighbors. Subsequently, we compute the Kullback-Leibler divergence between the category distribution and the contrast map is denoted as CMJ. The contrast score is denoted as CSJ. To enhance the prototype summarization ability that can help identify unseen classes during inference, we prefer selecting samples that are distant from all category prototypes. For the unlabeled image, we calculate the distance between each pixel and category prototypes, producing a distance map DJ. To identify samples far from all prototypes, we apply a minimum distance maximization approach, aiming to select the sample whose distance from its nearest prototype is farther. Therefore, we calculate a minimum distance map DMJ. The prototype score is calculated by averaging all its involved pixels on DMJ. We combine uncertainty score, contrast score, and prototype score to jointly select samples for annotation. Intuitively, we aim for samples with higher uncertainty and diversity, while also enhancing the summarization ability of prototypes. Therefore, we apply the min-max normalization to scale scores uniformly. The final query score is defined as QSJ. To evaluate the effectiveness of our method, we conduct extensive experiments on two pathology datasets, TNBC and HPBC. We also extend our method on a natural dataset, PascalVoc2012, to further verify its effectiveness. We compare AcZeroTS with SOTA active learning methods on the three datasets. The experimental results show that AcZeroTS consistently outperforms existing active learning approaches across different datasets, while significantly reducing annotation costs. We analyze the effects of each query strategy in AcZeroTS on the TNBC and HPBC datasets. The results indicate that using all three criteria together consistently achieves the best segmentation performance across all cycles and datasets. We also present sample visualization results on TNBC at the third active learning cycle. Compared to SOTA active learning methods, AcZeroTS can more effectively detect unseen tissue regions, as well as achieve better segmentation. We finally discuss the effectiveness of our ZSS model ProZS. We compare ProZS with SOTA methods for the ZSS task. From the table, we can see that ProZS achieves superior performance for tissue segmentation, particularly on the unseen classes. In summary, we propose AcZeroTS, a novel active learning framework for zero-shot tissue segmentation in pathology images, which is built on a prototype-guided zero-shot segmentation model ProZS. AcZeroTS can predict unseen class tissues with limited annotation budgets, which shows promising potential for detecting diverse tumor microenvironment components in pathology images. The experimental results on two pathology datasets, as well as a natural image dataset, demonstrate the superior performance of our approach in comparison with the existing studies.